Hey, everybody.
Hey, what's up, guys?
Welcome to another episode of Eigenbros.
Indeed. So we're doing failed physical theories today.
Failed. Quotation marks.
Yeah.
Air quotes.
Yeah, the Wikipedia has a little better title called superseded physics.
Yes.
We're just going to use that title as the clickbait for this video.
Yeah. We kind of give a brief rundown of like a little quick survey of the history of like just theories in general.
Yeah.
And then kind of get into the real kind of interesting ones. Terence, you brought up basically the more famous ether kind of
Yeah,
model.
I think actually technically you brought it up. But
Oh, well, I eased into it.
Yeah.
But yeah, and then we talk about some theories in quantum that were like tried out for a little bit, and and then we kind of just so that the first half is history, the latter half is kind of like those little quote unquote failed theories and or theories that were superseded or kind of failed to answer bigger questions. But hopefully you found this illuminating and interesting.
Well, they didn't watch it yet, but they will find it.
Oh, true. Hopefully you will find this. True, very true. But yeah, hopefully you thought this was this is something that's interesting to you. So, yeah.
All right.
I'm still can't articulate that well.
Yeah, you're still using past tense.
I'm pulling this. It's because I'm thinking ahead. It's because I'm thinking about the outro. I'm sorry. Yeah. Anyway.
But yeah, guys,
Stay
just
tuned.
make sure you like, comment, share, subscribe, and look, you got me
Past
doing it
tense. Yeah.
And then check out the website eigenbros.com. Check out the Twitter Eigenbros, Instagram Eigenbros, and then also TikTok Eigenbros 2. And we'll see you guys in a bit.
3, 2, 1.
Welcome, ladies and gentlemen.
Welcome to another episode of Eigenbros. Today,
Back in black.
Yeah, Back in Black. Back in Black.
Who sings that?
AC/DC, yeah.
Mm-hmm.
Yeah.
They're good.
They're
Classic.
all right. They're pretty decent. They got a couple bangers.
Yeah.
You
remember my philosophy we were talking the other day? If they've got more than 2 songs, then I'm already sold. I'm already sold on you as a band.
Yeah. No, they're great. They're AC/DC. I'm kind of wondering why they decided to go with an engineering name.
I'm sure there's an interesting story, but
yeah,
I don't know.
Watch the lead singer's like a physicist or something.
I think it might have to do something with Tesla versus Edison. Yeah.
Maybe.
I think I actually read something on this a long time ago, but I don't want to say because I have such a bad memory. I don't want to pollute the already rife with misinformation internet with any more stuff. So
yeah. So as you can tell, today we're talking about where band names come from. No. Today we're talking about failed physical theories. And this
Wiki actually had a better title, I think.
What?
We'll use the failed as a little clickbait for the video, but
of course.
Superseded was a good one.
Oh.
Because usually physical theories, when they're around, they typically get superseded with something. They're not necessarily failed. Although some of the ones that, maybe that both of us have in mind are kind of failed in some sense, but I think a lot of them get superseded.
Yeah, a lot of them do get superseded. They're mostly like there are some examples that still exist in our textbook as historical how would you say,
like placeholders?
Yeah. They're still good to a certain point.
Yeah.
They're approximations and they're decent for that, but they fail in certain limitations, or they don't really give an accurate picture as you go to take it to certain limitations.
Right.
But yeah.
And like even the Newtonian mechanics, you could call like a superseded physics theory, right?
True.
Technically, but it's a great approximation. So I would kind of put that in a different camp.
Yeah.
On its own, because it's still useful, right?
Yeah, because for me, failed theories are some that are just, they're good. Like it's more, it can't answer most things. It can answer some things, but not most things. Do you see what I'm saying? And I have some examples.
Okay, so it's got a threshold of explainability. Can you say that?
Yeah. Okay. Because like the ones that we use still today, like Newtonian mechanics, we still use that because it's still useful in solving most problems. Right. In
Newtonian land, for sure.
Yeah.
Extremely useful.
Yeah. So, but there are other instances where, it's really not useful to talk about that at all. So, So yeah, I do have some examples though to give.
Yeah, man. What you got on your list? If you want to start, should we start breaking it down?
But should we? I guess maybe we should take it more like a historical thing because because Newton was like, I wouldn't say Newton was the first guy, but you have to go back to antiquity to like the Greco-Roman times maybe even. Because you have to think about like
the math days and the philosopher-dominated days.
Yeah, because those guys were first, the natural philosophers. Those were like the early physics guys. Just pontificating. They kind of had
their toe dipped in physics, right?
Well, they did. The modern incarnation of physics is philosophy. Basically, I like to think of physicists as like philosophers with analytical tools.
Right. I thought you were going to say philosophy coupled with math.
But yes, that's basically what it is.
Yeah. It's pretty accurate, I'd say, right?
Yeah, but those guys didn't have. Well, they had a conception of what math should be.
Yeah,
you know what I mean. Yeah. They had this like preconceived notion of like beauty and
thing.
Yeah. I mean, very well. Like we're talking about guys like Pythagoras who had like a cult.
Right. Was that him with the fucking what is it? The like geometry cult, what was it?
Yeah.
Oh, the Pythagoreans.
Yeah, the Pythagoreans, but like they had
they like executed some guy because he found that square root of 2 was irrational or something. I don't know if that's true. Please don't quote me on that, but I think that's either like a rumor or one of those kind of like fantasy stories that's out there. I don't know.
Yeah, I would agree. I would 100% believe it because those guys had like an idea of they were obsessed with sacred geometry and like these rules of how like nature is supposed to be as opposed to more of an empirical scientific worldview approach.
They had like a vision of nature and were fitting it into that little fucking beautiful box,
and that set back science for a very long time.
But it makes sense because it also progressed it at some level, right?
You geometry like or math, the exploration of like how lines and points and what interesting like rules you can make or say and stuff to solve certain problems was like huge.
Right.
But I mean like
the physical nature of it was extremely powerful. And it's very natural for the human brain, right? Because we're spatial creatures. This is why I love geometry so much. You already know, Juan, that I'm like obsessed with geometry.
Yeah.
I try to put it into everything in physics, just because it's how we perceive, right? So, and when you're a person who operates on a lot of intuition, geometry is like a cheat code in many ways because you can visualize things before you even need the equations.
True, very true. Yeah, it's like it kind of goes without saying, like geometry was kind of like this one subject, and algebra too was this one subject that was born out of necessity, right? Because like you go back to the Egyptian times when like property started becoming, or land allocation for property was starting to become a popular thing, and so farmers had to be, for you to construct or for you to have a certain crop yield, you had to calculate certain area and approximate how much of an amount of wheat or something that you grew. And so you'd have to use like length and width and these concepts, these bigger concepts. And then like you're solving for a certain quantity because you don't know, but you have these knowns. And so the theory of algebra and everything gets developed. And so like you slowly build up to these philosophers using these kind of tools, but the thing is, like it kind of, I don't think any real physics starts to get done until maybe Newton, right? You get like out of geometry, you get these guys.
Well, what would you consider real physics?
Like really analytical. Like calculus was like the real analytical backbone of physics, and that's kind of. Yeah, because we had algebra and geometry for a long time, and we were able to solve problems in optics and stuff. Optics is pretty much the study of like how light rays move through space and how they bounce off of objects. So that was like a natural extension to geometry, right?
And that kind of makes sense, I guess, because guys like Galileo and I think Galileo
preceded
Newton's,
Copernicus and
right?
stuff. Yeah.
So I think Galileo invented the first telescope. So that would make sense. They'd interest in light rays.
Yeah. So a lot of those guys, they were able to use those basic ideas that were kind of like, or math that was built in antiquity and stuff. Now there is an important result, because back then anyway, those guys that tried to describe atomic theory, they kind of what did they try to describe as atomos or some
Atmos or something, but they called it, like, I think it was like Democritus or something called it the irreducibles or something. It's like he basically came up with the idea of an atom by saying there's this irreducible quantity eventually as you get smaller and smaller that cannot be separated.
Yeah. This indivisible fundamental thing.
Yeah.
Right?
Yeah.
Which is crazy. That, like, it's kind of like a big deal to come to that conclusion out of just...
But those guys were coming up with so much crazy shit. It's like eventually one guy could have come up with that, right? Because, like, think of Aristotle with his whole theory of the elements, right? Yeah. He's saying that there's, like, units of fire and units of ice and things. It's
True.
It's like they're coming up with all kinds of stuff just based on thinking. It's like, okay, you could see someone conceiving of something like an atom.
Yeah.
He just happened to be right. But his knowledge was not founded in anything.
Yeah. That was like a rudimentary kinetic theory of, like, basically kinetic theory of atoms and stuff. How, like, because if you...
What do you mean kinetic theory?
Because, like, you're extending... Kinetic theory is kind of like this... You think about most matter as jiggling balls.
But did he say that?
No. But I'm saying, like, you can think about it as an early model of that. Like, if he extended it to, like, everything is jiggling around us, and, like, you know, that's how you get, like, things have temperature because they're jiggling.
Some good shit if he's coming
If he's connecting those dots, that was just insane. Like,
that's a good ass peyote.
No, because, like, kinetic theory is actually really useful. Even to this day, I learned it in. It felt like when I learned it, I felt like I was unlocking some secret knowledge of the universe, because, like, you can describe so many things using, like, basic kinetic theory, like, oh, things are hot because the atoms are jiggling.
Yeah.
You know.
But then you always see the correction where people say, which kind of annoyed me at first, because I was like, they say temperature is not atoms moving at faster speeds.
Oh, right.
And I was like, then what is it then? But I guess the more nitpicky way to say it, it's the kinetic energy of those particles.
Yeah, it's like the average kinetic energy.
I'm like, if you get that it's atoms jiggling, that's almost like half the battle, right? But I guess it's like, for the pedants out there, that you can't say that.
No, but that theory, that's one of the first theories that I think, like, you can look at and think, like, oh, that's a pretty good approximation, but I'm getting ahead of myself. Anyway. You know, you had those guys, and they Archimedes was one of the few dudes too who kind of proposed. We still use one of those laws today. It's basically buoyancy, right?
Yeah. His whole density. He invented the concept of density, or like
how, like, water is displaced in a certain way, and how it relates to basically the area and all this stuff, and
that less dense objects will float in a higher density liquid.
Yeah, really cool stuff. I think they were trying to do that to see. I think a king had paid one of these guys to figure out how they could determine if gold that they had was fake.
Yeah.
Right?
Yeah. It was a fake crown or something versus a real crown. And then Archimedes came up with the concept of density, his whole eureka moment. You know, it's the whole classic story. And then he found out, I think, that the crown was fake, and then they just killed the guy.
Beautiful.
I don't actually know if that's true. That's my story. That's my version of it.
Yeah, that's the Game of Thrones type of story where they get beheaded for miscalculation.
So bad physics has dire consequences. Guys.
I mean, it's kind of true. Like, a lot of physicists and mathematicians back then were hired as sort of mages or wizards or something, because they were like, make these weapons happen for me, and then, you know, like, they had to build catapults and stuff like that in later ages. But
it's basically like the real life movie trope of the smart guy, like, you're smart, you can do this, you know. Figure this out.
Yeah, you're a virgin, figure this out. No, I'm just kidding. Please don't attack it. That's a joke, okay? Anyway, anyway, get into the more serious stuff. You know, you go through the ages, and things don't, you know, you get Copernicus, you get these other guys that are studying, like, the motion of the planets, and it's pretty, they're doing a really great job. Yeah, Kepler, they're starting to figure out orbital motion and stuff, and And then they reach a limitation because I think the math starts becoming insufficient, at least the geometrical versions of it.
Yeah.
And
it's too complicated.
Yeah, it's too complicated for the rudimentary tools. And so I think at the time we're talking early 1700s or something.
I can't give you dates.
Can't me either, yeah. But I think
it's probably around that.
I'm spitballing here.
Yeah.
And yeah, so around that time, I think a couple mathematicians, I think Leibniz and who was the other guy? The calculus dudes? Leibniz and
who?
I forget his name.
Newton?
There was another guy. No, besides Newton. I think there were two mathematicians, and then one of them's Leibniz, and then Newton, of course.
I don't know another.
But Newton was a kind of funny guy. Like he had, while he was kind of inventing calculus, I think it was also during a pandemic.
Was it really?
I think so.
Oh, no shit. Black Plague?
Yeah. I don't remember, but it was definitely also during a pandemic, if I remember correctly.
My history's garbage, so yeah, I'm not even gonna.
But no, it was he had sort of made calculus with his famous publication, what is it? Principia.
Yeah,
what is it called?
Principia Mathematica or something.
Yeah, which is Latin for I don't know what I'm doing. No, I'm just kidding.
Latin for I guess.
This is right. No, but it's he that was like groundbreaking, and I think there's a lot more collaboration going on at the time. I think people don't realize that a lot of those guys back then they loved talking to each other through like mailing and stuff, and you also had science journals that would come out, and people would share information through those avenues and stuff. I mean, truth be told, science was a rich man's game back then.
Yeah.
And so a lot of those guys were high class and yada yada yada. But anyway, Newton had a number of failed theories, didn't he?
Oh yeah. Well, Newton was basically a part-time physicist and spent almost the majority of his time on finding the Philosopher's Stone and all of this other occult magical bullshit, and was obsessed with God and religion. He was a full-blown crank by every metric. Alchemy, I mean, you name it.
Yeah, I think he was trying to figure out how to turn mercury into gold.
Yeah, or lead into gold, maybe.
Lead into gold,
Which is probably why he also died.
No, I thought he died of mercury poisoning.
Was it mercury poisoning?
I think it was mercury poisoning.
Okay, well, the thing is, you can turn lead into gold. I don't know if you can turn mercury into gold.
No, but I think that's what he was trying to do.
Okay,
and
that sounds hard though.
Died of mercury poisoning. but yeah, he. Yeah, he was famous for just having really bad theories. I think one way he thought of curing the plague was, and I think this was brought up on an episode of
Mythbusters or something.
Of It's Always Sunny in Philadelphia.
Okay.
I don't remember exactly, but it was just like he had this kooky theory that you had to take like rat organs or something. I don't know, something insane. And I was just like, okay, we have one of the smartest guys. I think he just had cabin fever. I'm gonna be honest with you. If this was happening during a quarantine episode where they had the plague or whatever during the time, he was just losing his mind. I think it was worse,
and all that mercury was finally dipping into his bloodstream. Yeah, I could see it.
The psychosis of not only being in quarantine and then the induced psychosis through basically lead pilling himself. He's just like dumbing down his IQ, but anyway,
he's going full blown crank territory.
Yeah. But yeah, it was good enough. After that, I think is really when physics started taking off.
Yeah.
You had then you kind of had the tools to understand thermodynamics a little bit better.
All these things. Calculus was just such a critical invention. I mean, that's really one of the biggest reasons why physics got.
Why do you think it made it so important to development of physics?
Just, man, it was just so critical because
what are these? The two basic rules of calculus, for those of you that don't know, are basically the derivative, which is like the slope at a point, and then the integral, which is the area under like a curve of a graph.
Then all those, you can say underneath that is the whole concept of the limit.
Yeah, that's the more fundamental, juicy bits.
Yeah. And that is just such a huge thing in physics, it seems, because in physics there's so many things that are just like rates of change of differential quantities, and just also the whole Leibniz notation, being able to work with mathematical concepts in that way was just so critical. It's not obvious at all that it would be that fruitful, in my opinion, but I mean, calculus is physics, basically. Like, all physics is dependent on calculus.
Yeah.
So,
if you're still out here in the streets using algebra to do calculus, to do physics,
you can do it, but like,
it's not illuminating.
No, and also, well, it is, but also it's like not even real physics, because you honestly can't even come up with certain equations and things, really. Maybe you can come up with some. I'm trying to think of like the projectile motion equations.
Yeah.
You can maybe from first principles, because you can say like, oh, I can see that this is following a parabolic arc, so I know it's a quadratic equation of ax squared plus bx plus c form.
Yeah.
But even then, it's like with calculus, it's so much easier to see where those derivations come from, and it's very natural.
Exactly.
And you just get so much out of that. I mean, yeah,
it's more fundamental. It feels more fundamental, right?
Yeah,
It feels like more first principles kind of stuff.
Right. It's like you actually get an understanding of how that manifests.
Yeah.
Whereas with the algebra, it's almost like a little bit arbitrary.
Yeah, exactly. And yeah, so I would say that the reason why besides what you're saying, like calculus made physics seem more like you can use first principles more. You're able to use certain axioms and then build off of that. And
certain things just are way more. I don't even know if I can say they're. I would make the claim that some things aren't even possible, but to be safe, I'll say things are just so much easier and simplified with calculus too.
I agree. Yeah, it's. I would say that the thing that made calculus really important to physics, besides like the testing limit things, because that's basically what physics do. They kind of take things to the limit, but but just how easy it is to, just how much more intuitive it kind of is. That's kind of like the biggest takeaway for me. Because doing physics with algebra was not intuitive to me. It I don't know why, but maybe it's a personal kind of like thing. But anyway, it was so fruitful that you basically had built modern physics on the back of Newton and Leibniz and all these guys that helped develop calculus to what it is today, or just the idea of it. And so,
So I mean, it's very, very good. But I guess to switch gears a little bit, Juan, what are some of the failed physics theories that were on your list? Do you have any?
So we build up to the modern era now, and like we get to thermodynamics and. There's some stuff there. I think they basically build on the kinematic theory of like gases and stuff, and how you look at like phase transitions. Those are all actually pretty good. They're I don't think there are any famous failed theories there, but this is like towards the end of the 1800s, where the engineers are studying like
and people were really obsessed with actual empirical data at this point too, because it was the whole rise of the Industrial Revolution. We actually needed this stuff to work, so people were really concerned with empiricism and actual experimentation and doing things in real life. So actually the theories and stuff were probably really ugly at some point. They're just like, it works, so we're just going to use this, right? As long as it works. Then it got cleaned up.
Exactly. But at the time, you had Einstein. Einstein was around at that time, and then Einstein and all those guys at the end of the century, and in the 1800s, they were trying to formulate. They were starting to dig deeper about like, atoms and how they make up the world, and are atoms in how would you say? Can they be broken down into more fundamental pieces? Because like, the study of thermodynamics and stuff, we kind of had to like look at different elements and stuff, because like in the industrial age, like you started looking at elements that would produce the most efficient like combustion or kind of process, like
Yeah.
You had to look at different chemicals and started looking at elements, and then your periodic tables getting like refined and built, and
right. There's a lot of empirical data being generated during this time. Yeah.
And so a physicist's job is to kind of unify, find trends, find principles that you can use to basically make this easier to digest. So
and to kind of universalize or generalize these systems.
Exactly.
Right?
So, at the time, I think quantum mechanics was, in the cross between 1900 after the 1900s, like around 1906, I want to say. People
I can't confirm, but
people
okay.
pinpoint this paper, the photoelectric effect, as like the start of quantum mechanics, kind of. Because this is where
Did they really say photoelectric effect?
Yeah, I think so.
What about the whole black body
that too.
ultraviolet?
Oh, that's a good
catastrophe?
point. Yeah. Did that come after or before?
I feel like it came before,
right?
Yeah,
because probably because this has to do with thermodynamic stuff, so that makes sense.
And it also has to do with like the whole beginning of the atoms. People kept revising the atomic model, and then the whole thing with Bohr saying, "Oh well, the energy levels they can't be, they can't be, what did you call that?
What's the word?
They have to be discretized."
Oh, gotcha. Yeah.
So
yeah, and it constant adjusting of models and stuff. But at that time. That's when all the people started coming up with janky ass models because we had so much data, right?
Right.
We had so much data because of the Industrial Revolution and just pumping out science and stuff, and
testable science,
and yeah, so we started like saying, okay, well maybe maybe we can describe. At the time, you can try to describe quantum mechanics. It comes a little later, but because we're still building a catalog of data. But I think at the time, Maxwell's equations, E&M, was like a huge thing too.
Yeah.
Right?
Because it was getting finished off, right?
It was the bow was being tied.
Yeah.
And I don't think there are that many. In fact, when calculus was invented, if you look at Maxwell's equations, if you look at the E&M equations before calculus.
Yeah.
Ooh,
nasty,
boy,
gnarly.
Have you seen them?
You're talking about when they were just Ampere's law, Faraday's law, and all that stuff.
But they didn't have calculus, so they didn't have any cross product bullshit that you see today.
Are you talking about when Maxwell was formulating it, or even before that?
Because you had E&M laws that they knew, but
they were all just jointed. Like Maxwell, they were like Ampere's law, Faraday's law, Gauss's law, those kind of things.
Yeah, Biot-Savart stuff. Like you had all these like laws, but calculus did not. Like they Maxwell is the guy that makes Maxwell important. The thing that makes Maxwell important is like he beautified.
And he actually, I discovered this. He actually didn't really beautify it fully.
Oh, really?
Because Maxwell beautified it in a way where he used quaternions.
The hell does that mean?
So quaternions are the things that are, if you remember, they have the IJK. Components.
I thought you were talking about these little alien people that live in like a certain subdimensional space or something.
Is this a video game reference or something I'm not knowing?
I don't know. It just sounds like
or just from
alien...
the imagination of one.
It is. Yeah. There are quaternions in my brain that make things move. No, but
yeah. So he had some. It was beautified, but it was still like 20 equations or something now, and. The thing was, they were all in like different dimensions. They had a spatial part of it.
Yeah.
So it was almost, you can think of it as like someone saw that, you can actually simplify this even more if you use the gradient operator. So I don't know who did it, but someone else actually invoked the gradient operator instead and made it so that it was this 3-dimensional vector.
Gotcha.
And you can actually simplify it even further.
Yeah.
So Maxwell beautified it greatly, but then someone else took it down from like 20 to like 4.
Yeah, and that's what I mean. Like, and it doesn't. The mathematical representation today is beautiful because of calculus.
Yeah.
Like before, I think it existed. It was this ugly mess of, like, how do you even? Because I don't think
the connections weren't even there.
Yeah,
because
just
a bunch of random equations.
Yeah, and I think they didn't have like good language of what a cross product's supposed to be. Like vector calculus was like so rudimentary. I think, if I remember correctly, it was kind of like they were still trying to figure it out. And
yeah. I'm not sure of that history.
But we're spoon-fed this complete package.
It's so easy for us nowadays. Like, we take it for granted.
Yeah, we kind of do. I 100% do. I will say that I do. But Yeah, so like E&M was, I don't remember that many failed theories for E&M besides this prevailing idea at the time that there was an ether of sorts that carried, because they were still trying to figure out like, oh, light is a wave.
Right.
You know
right.
what I'm saying? Like,
yes, this is one of the ones on my list. The luminiferous ether, as they called it. It's even a mystical sounding name.
It is. It is. 100% is.
Like it's something I would expect to see in like a book on Greek mythology or something. But yeah, the luminiferous ether is basically the medium in which light travels that was claimed. Who was the one that came up with it though? It's an old theory that's been around for a long time.
It is, because they were trying to answer what E&M, how do light waves, because they saw that waves, could carry, how would you say, like, usually when things travel through, like air has a medium of atoms of.
Well, no, air is the medium.
Air is the medium.
So sound has a medium.
Sound has a medium. Thank you. I was trying to articulate that better. Thank you, Terence. But you get what I'm saying. They had this base of knowledge where their intuition was telling them, oh, sound has the medium of air to travel.
Right.
By analogy, it should extend to light as well, because it's also a wave.
And it's almost kind of a natural human extension, because we kind of see air like as humans, like, oh, there's nothing here, right?
Yeah.
But then it's like, oh, when you become, woke, you start to realize that actually air has particles, and it has constituents of oxygen and nitrogen and all this stuff.
But that's the woke take. That's when physicists got woke to the air around us, and they were just like saying like, the world in front of you isn't exactly what it is.
Exactly.
And they were like presenting people the red pill, and people were like, what the hell are you talking about? But it was this natural extension to the luminiferous ether.
Yeah, so they basically then said, they extended that to saying that, oh, space, that has it has a medium that light travels through. It's instead of a vacuum, it's a plenum, I guess, which is the alternate form, or the antonym to vacuum. So it's got a plenum of ether, basically, that we can't measure in any kind of way because only light interacts with it. And I think only one of the ether forms actually stuck. And
which one was that?
I'm trying to remember who it was.
Because a famous paper got published.
I want to say Huygens, but I'm not sure. I don't want to get it wrong.
Yeah.
Huygens is probably wrong.
Okay.
So don't take that in your
Don't
mind.
worry about it. Yeah. Facts don't matter here.
Yeah.
This is a podcast.
As long as I preface it by saying I don't fucking know.
It's history. Come on.
Yeah. But anyway,
Yeah.
So one of those stuck, and it stuck for a long time. This was actually way back, during like Copernicus times and everything. Which was before Newton. So people were thinking about the ether and accepted the ether for a very long time. I mean, well into the 1900s, like during Einstein's time,
right? Yeah,
which is actually
100%.
kind of crazy. They just didn't really question it that much. They just said everything that's a wave needs a medium. Therefore, light is a wave as far as we notice. I forget why they thought light was a wave.
Because at that point, Huygens and those guys, they had already done those experiments, the slit experiments, where they were already saying, "Oh, light, you see."
But
this
the double slit
diffraction.
was Young.
Yeah, and Young as well. But that
was he before Einstein?
Yeah.
I don't think so.
No, he was around that time.
Okay, yeah.
Yeah, I can pretty much guarantee. I can look it up, but yeah, go ahead.
Yeah, but the guys who came up with the fact that light was a wave, they're like way more ancient than Einstein.
Yes.
And I have a feeling it has something to do with like, well, I don't know. I can't remember. I don't want to say the wrong stuff, but it definitely probably had to do with like optics and things like you're saying, because you're mentioning that optics was actually preceded even Newton, due to guys like Galileo trying to invent the telescope and things like that. So I'd imagine there were some wave-like properties that they got from that.
Well, yeah, literally the first experiment was performed by Thomas Young in 1801.
To prove that it was a wave.
Yeah, they saw that wave, that light.
Yeah, he's
behaved as a wave.
1801.
1801. Yeah.
Oh, wow.
So that's what I'm saying. Like, they already kind of knew that light behaved in this matter.
Okay, and then we extended it with quantum, I guess.
Yeah, we did.
Interesting. So maybe he didn't even know about the fact that once it gets measured, it collapses.
No, it came in the 1900s.
Oh, wow. Very interesting. So, damn. Yeah. So Young actually performed the experiment without even knowing it was a particle. So then really the thing that started to shatter that whole thing of the ether was when Einstein came up with the photoelectric effect, and he discovered that exists, and it quantizes light into particle like packets. Mm-hmm. So then it's like, okay, what the hell is light? Is it a wave? Is it a particle?
Yeah.
What is it?
Yeah.
So then all these misconceptions about light started to get uncovered, and people started to basically, light was getting picked apart.
Yeah, you basically started fundamentally questioning what is light, what is, because we had
Doesn't
taken
even need a medium.
Yeah, we had we had taken all these things for granted.
Yeah,
for so long, and it's like, but we knew certain things that were sort of indescribable in some way. Like Thomas Young's experiment already showed that light is a wave, and Maxwell's equations I think made that all beautiful. Like by that point, I think late 1800s, I think Maxwell's equations was already like pretty much done, right?
I'm not sure.
I want to say
I can't make the claims. I'm not sure.
I'm gonna die on this hill. I'm gonna say yes. And
Oof,
no, because because you had this. I think because Einstein came to this conclusion of like the speed of light is constant because he had done certain calculations, where necessarily, you get that v the time dilation and stuff like that. Well, he was using Maxwell's equations in some form or manner.
Well, but Einstein's also was. I think Einstein's was mostly motivated by experiment, though.
Yeah.
Because Michelson and Morley actually did that whole, Michelson interferometer.
That was the big experiment.
That was the big basic proof that light speed is constant, right? Because when they actually measured it, that no matter what, it keeps coming up with the same number.
Yeah.
So.
And that was also the paper that. Wasn't that the same paper that proved the ether was kind of bunk? Because they were saying, well, the ether, if we're going through the Earth, the ether, we're either going to be parallel or perpendicular to it, and like.
Oh, I didn't get this deep with it. I forgot to actually go that deep with it.
There's a famous paper.
Why.
I think it was they were using the Michelson for. I think that's the same thing, but they were. They were saying, if the ether exists, then at some point we should observe, like you're saying, the speed of light slow down if we're perpendicular to it at some point. Right? Like if the Earth is rotating around the sun.
What if it's just what is it called? Anisotropic.
Yeah, like that was one of the counter arguments to that. But like the speed of light was like constant, like you were saying. They measured pretty much throughout.
Interesting, but they were expecting not to.
Well,
the directionality was important.
They were trying to say if the ether exists, then you should observe. If light needs a medium to travel, the Earth is rotating, so there's going to be a point where the Earth is perpendicular to the path of the ether, and you should observe some drop in the speed, because at some point
not convinced by that because you can have isotropic medium.
Sure, I mean, look, dude, I literally heard a professor like say before that they think in some form maybe there is an ether still, and I was like, what? And I was like,
is he a crank or?
I was just like, what? I was like, no, but they were basically making the argument like you're saying, like it could be isotropic or whatever, like it looks the same everywhere, blah blah blah.
Yeah.
But as far as we're concerned, empirically, there's functionally, there is no ether. And so
it may not be necessary.
Yeah.
Maybe it is. I mean, still, I guess it could be. I don't know. I didn't see anything debunking it, and I didn't look into it enough to where I can debunk it myself.
It's debunked.
It is debunked, but of course, I like to convince myself first.
But that was one of the big models for like for light, how light behaved and stuff, and so. You needed a medium that kind of got thrown out the window because, it did. The Michelson-Morley experiment showed that you don't necessarily. It doesn't. The speed of light is constant, pretty much. And Einstein kind of like made it all nice and prettied up, and so I think that's when he kind of moved on to general relativity. But I want to stick to quantum because quantum is the one that's still. Like relativity and all that's kind of been fleshed out, I believe, like, to its fullest extent. So I don't know if there are any theories that,
Well, things break down at black hole level, right?
Yeah, but
and
I'm
then
saying...
also there's things with the cosmological constant, which is another thing on my list.
Oh, really?
Hint, hint. Yeah.
Okay, well...
Spoiler alert.
Okay, yeah, go ahead. Talk about that one, because
Okay.
I was gonna move on to quantum, but yeah, go ahead.
Okay, yeah. I think we don't show relativity enough love on this podcast anyway, because we always talk quantum.
Yeah,
so
we're
let's go a little bit
condensed matter
towards...
theorists.
Yeah, but let's go a little bit towards relativity. So relativity has the cosmological constant, right? I mean, you're familiar with it, Juan. I'm sure a lot of the audience is familiar with it, but Einstein called it his biggest blunder, basically. But it was his biggest blunder because he inserted it for the fact that he was trying to get the universe to be static. So Einstein basically came up with this equation called the Einstein field equations, and it's got some metric tensors in there. It's got a Ricci tensor, and these things all are there to basically describe the curvature of space and the geometry of space-time, basically. So one of the problems was, though, with this theory, you actually get a flaw where when the universe is in an equilibrium, you actually can get a contraction or expansion of space. So he's trying to make it so that in the beginning of time, you had this equilibrium position of the universe, but it's unstable. So you get a contraction or an expansion of space. So he basically inserted the cosmological constant as a correction to make it so that the universe is static. But then his buddy Edwin Hubble, comes back and shows Einstein some things related to redshift of galaxies, and actually was basically showing that when galaxies get redshifted, it means that you're actually stretching. When things get redshifted, it means that the light rays are actually getting stretched.
Yeah.
So, and that means that there's actually an expansion. Is that true?
Yeah, because you get a longer wavelength.
Yeah, so there's an expansion of space. So actually Einstein's cosmological constant is not necessary in that case, because his theory was actually correct as it was initially, where you could allow for the expansion of space. But then, of course, now people kind of still like the cosmological constant a little bit, because I think there is a little bit of discrepancy where you should get some kind of particular number from the cosmological constant. So I think they're like tweaking it.
Yeah.
And I think that comes from quantum field theory. There's a mismatch between quantum field theory and the cosmological constant. Actually, there's a giant discrepancy.
Oh.
It's like one of the biggest failings of these theories.
Oh, gotcha. So even then, right now, it's still a work in progress.
Yeah, so the cosmological constant is a big work in progress, because people still are uncertain about how the whole expansion of space works. And I'm sure, I have a feeling, don't quote me on this though, so this is another warning alert.
Yeah.
But I have a feeling that it has something to do with dark energy, and possibly dark matter, which is why that there's some error in there. Of course, astronomers, please correct me. Laymen, don't take that. Don't take that and run with that. Just keep it as a potential in your mind.
Yeah.
But yeah. So that one is another kind of failed physics theory, but actually turned out to be useful in some sense.
Yeah. That's kind of how it works out, because like when we were trying to describe like electrons in materials, you have like this, even in condensed matter, you see this all the time. You have like the Drude model of like, you have so many models in condensed matter that it's like, all right, so these models are all good to a certain point, but there's so many, like, and I just named the Drude model for one, just because.
Yeah, what does that have to do with like the
electron and like heat capacity and stuff,
dispersion relations and whatnot?
Yeah, basically,
Okay.
and it's just like it depends on the regime that you're looking at and stuff, and then you also have different models of like what kind of wave functions you can use. You already know, like the block model of like wave functions, and the type binding model of like
it's all coming back.
Yeah. So you think about all these
Ising
different
model.
models. Yeah.
Yeah.
You have so many little toy models that physicists is built to try to describe such a disparity in such a huge number of physical systems that
Right.
Naturally, ideally you want to find a one size fits all, but
but they're all trying to describe different pieces of the puzzle, basically.
Yeah, maybe one day we'll have just a nice, beautiful little thing.
We need a condensed matter Ed Witten to make the M theory of condensed matter
Yeah,
physics.
exactly. Yeah. But this kind of leads me down to the quantum path, because, Einstein, the Nobel Prize that he got was for the photoelectric effect. and he kind of spurred this this idea that maybe particles, maybe other particles are quantized. Like what is the atom made of? Is it made of other fundamental particles and stuff?
Mm-hmm.
And so people started probing atoms a lot more and the atomic structure and stuff. And so you started delving into what makes the electron and the atomic system so interesting, and give all these weird characteristics. And then you basically get all these weird experiments that come out.
Is this the whole particle zoo we're getting into now?
Yeah.
Okay.
And so like you get all these weird experiments, and then you start building a sort of model for basically atomic physics, which is, they call it quantum mechanics, but all it means what they mean by quantum is like things that are just
small,
discretized, small.
Okay, yeah.
Because like you had continuous energy before. We in the classical regime we deal with continuums. We deal with nothing that's really energy is not really. Energy is pretty continuous for the most part.
Right.
But in quantum mechanics, like you get like these little bits of energy.
Right. The Planck's constant starts popping up everywhere.
Yeah, exactly. Exactly. So
H bar for those not familiar.
And this doesn't really make sense to the intuition of a lot of physicists who were bred on continuous energy and all this stuff. And so
which Einstein was, because quantum mechanics was not invented during his times coming up.
Yeah, exactly. So the thing is, like, a lot of those guys that came out, like for instance, Schrodinger, right? So Schrodinger, he didn't like this. He didn't really like quantum mechanics.
That's hilarious.
No, I know.
Literally, his equation is like what you use
for the entirety of beginning quantum mechanics.
Well, he didn't like the collapse postulate stuff. A lot of physicists didn't.
Yeah.
They had to come up with
interpretations.
They had to come up with the interpretation of the Copenhagen interpretation, which is like the one we use today, or is most popular today.
And actually, physicists still don't like the interpretations now. So there's still hot debate over what's real.
100 years later, and we're still... it's this wave-particle duality, and that's kind of the Copenhagen interpretation.
Although Eric Weinstein
claims there's no wave-particle duality. He just says everything's waves.
I'd have to...
Yeah, I think because it is waves, but it's like boundary conditions in some form or manner. Like, this is kind of what Schrodinger kind of thought. So I'll elaborate. I'll elucidate more on this. So Schrodinger actually came up with an electromagnetic picture of quantum mechanics around 1926. So like quantum mechanics was actually formalized by 1930, I think, when von Neumann published his like book on like the theory of quantum mechanics. And if you go back to it, it's like nothing much has changed. Like, it's kind of nice. It's like it's still formulated, and you have.
That's not good and bad.
That's good and bad at the same time.
Well, I mean, like they kind of employed this. Like it works. It describes it describes what we see, but it's just math. Like it's just like we're using matrix, the formulation. You have the Heisenberg picture. You have which is the matrix mechanics stuff.
Right.
Using linear algebra, and then you have the Schrodinger picture where you're using like waves and stuff. Right. But anyway, Schrodinger, he believed that if the quantization of energy that led to basically quantum jumping, or like basically, quantum jumping.
What does that mean?
It's just like electrons that move up to like that when they're excited,
energy.
They move to higher energies and stuff. If it was true, it would leave him sorry for ever getting involved with quantum theory. So he was just like upset that he's like, this doesn't make any sense. I don't like discretized energies is basically what he was throwing a hissy fit about. But Schrodinger was basically trying to formulate a continuum picture of quantum. So it was guided by boundary conditions set by Maxwell's equations, and basically quantum theory. He basically got it he built like a wave function that solves his wave equation for the picture of an electromagnetically active hydrogen atom. So it looks, I'll show Terence this, but yeah, this is kind of the equation, and we'll post it up. It's got like
Okay.
It's basically using E&M. He's trying to combine E&M and quantum in some way, trying to merge the two, because naturally you're like, oh, quantum electromagnetic theory is continuous. You know what I mean? There's no discretization.
Okay.
And he's like, obviously, and that theory's right. Let's extend it to quantum mechanics, right? So this is what's interesting. He obtained with good results the dipole moments of the electrons at frequencies known to be radiated. He obtained the Zeeman effect and the Stark pattern. So if you remember the Stark effect for the hydrogen atom, with both like the non-vanishing components and the vanishing components, like the lines. He basically was able to, with this theory, he was able to basically show that the Zeeman effect and Stark effect were like true in his little picture.
Okay.
Which is like pretty damn cool if you think about it.
Yeah.
And he found it was so successful in describing the radiation amplitudes, electric charge densities, and other things that he basically was like, bro, quantum theory is just wave mechanics. There's no particles, no discretization,
Interesting.
and no quantum jumps. So, like in his like little picture of, he basically it's a perturbation theory basically, but it's like a perturbation theory to the electron and the hydrogen atom. He showed that collapse was unnecessary because he could explain it as a form of resonance. So what I mean by that is the quantization or whatever is basically like analogous to acoustic beats that are being produced.
Okay.
And that wave packets can simulate the appearance of point-like particles. So these beats look like particles.
Yeah,
they look
yeah.
like these little things. And yeah, his interpretation, however, failed to explain the particle nature of quantum mechanics over long distances. So Lorentz actually had
What does that mean?
and I'll explain. But
Okay.
Lorentz had realized this, that it couldn't survive the complementarity principle, which is that his wave packet treatment of the particle wouldn't it could not live. His acoustic beat picture couldn't describe why wave packets survive for such long distances. Do you see what I'm saying? Because any perturbation in the waveform would shear the wavelet and destroy its envelope. So this acoustic beat thing, like your little acoustic beat picture wouldn't describe why, like the photoelectric effect, like it gets ejected, but why does it still survive for over long distances? Like your little acoustic beat, any little like interaction with another sort of resonant phenomena or any interaction with other waves and stuff, it would destroy the particle.
Okay.
You know what I'm saying? Or it would destroy the
I think I
state.
see what you're saying. Yeah.
Yeah.
It's like a local theory kind of.
Yeah, because if you could think about it like that, like if it's an acoustic beat, it shouldn't like hold form, because like we know sounds, right? They kind of like are easily
Disturbed and
Yeah.
they bounce off walls and things. Yeah.
Yeah,
and then
yeah,
you also get like spots of interference or destructive.
Destructive.
Yeah,
destructive
so Lorentz
interference.
was like, bro, it's not gonna explain why, like a particle, like if I send a particle from here to over there, it's gonna look the same from my point to over there. But an acoustic beat isn't necessarily gonna look the same, especially if it's interacting with other stuff in the way.
Yeah.
It's gonna lose some information.
Yeah.
Like
yeah.
the amplitude will decrease, all this other stuff.
And what was Schrodinger's response?
Well, let me see. Well, Heisenberg basically delivered this crucial blow to Schrodinger's quantum mechanics and E&M interpretation, stating that the eigenvalues that he was able to get for the frequencies that he obtained were only allowed when the potential of the electron is basically a harmonic oscillator. So he was just like, it's kind of like not a real picture in his little basically view of it. He was like, bro, it's not a harmonic oscillator. And I don't know. That basically was like, everybody was shitting on Schrodinger at that point. My man was losing it. He was down bad.
That's pretty cool though that it worked out so well for certain things.
Yeah. Well, the thing is, what's interesting is though that De Broglie actually, or De Broglie, I can't even pronounce his name. Yeah. In the same vein, he tried to frame the results of quantized energies with that of a wave mechanical picture of Schrodinger. So he took Schrodinger's picture and was like, okay, let me try to extend this.
Mm-hmm.
And he had this sort of double solution interpretation that came out like a year later after Schrodinger. And he said that if quantum is a theory about waves and particles, there should be a representation of its evolution with a particle and wave component. So now, with the de Broglie picture, it was still governed by the Schrodinger equation, but it added motion of particles. So you now had a wave component to his solution and a particle component to his solution, or his equation, I should say.
Okay.
So, and then that, basically the de Broglie one also kind of like spurred the more famous de Broglie-Bohm pilot wave theory.
Okay.
So that was kind of the formula. Yeah, this was like the foundations of that. But because like the de Broglie picture faced the same shortcomings as Schrodinger, and it still wasn't a full quantum mechanical description of like what they were trying to describe. And so so like literally that theory was pretty much like shelved for, I mean, we're talking about 1927. It wasn't until the 1950s that Bohm pulled it back out and was like, hey, maybe there was a pilot wave that we can sort of use. But that's that's a more famous, like, I wouldn't say failed theory. I mean, it kind of is, because most physicists will say that there's certain quantities that can't, there's certain infinities that we can't, like we can't get certain finite numbers that we know exist in the Bohm picture.
Okay.
Like basically what physicists call renormalization. There's certain things that we can't renormalize.
I see.
So things go to infinity, and you're just like,
didn't even like renormalization.
He didn't?
No.
Explain.
He just said it was he said it was just like a shitty workaround or something.
No, not in those words, but I watched an interview of him and he didn't like it.
Yeah, Dirac is another famous guy of like him having weird, like we've talked about this, him having weird like leaps in logic, right?
And then he gets the right answer. And you're just like, why? That's so far to extend.
Yeah, what was that picture you were telling me about?
I was talking to you about the Dirac Sea. We talked about it on one of the podcasts before on I don't remember which one. I think it was one of the alien ones. But he came up with the concept of the Dirac Sea. And it was just like,
no, but also
coming up with this,
he
man?
also came up with the Dirac equation, right? And he had come up with all this weird stuff, right?
That's where it comes from, though. So he came up with the Dirac equation makes sense. So basically, he was trying to make an equation that looked like the Schrodinger equation, but it was a relativistic one. So he looked at the Schrodinger equation and said, okay, how can I make this a relativistic version of Schrodinger's equation? He realized that you needed matrix elements or something, so you had to promote like the operators or something. Again, preference. I don't know what I never actually studied the Dirac equation, so I'm not going to get everything correct.
Because this is QFT technically.
Yeah.
Yeah.
But he promoted something or had something where he changed it slightly and was able to get some answers. But then when he got some answers, he noticed he got energy values that were negative out of it.
Yeah.
So he was like, that's a problem. We don't see negative energies in real life. So then what he assumed that all of space was filled with electrons that occupied those negative energy states. So that
huge
yeah. So that you can only get things that have positive energy, because all the space was already filled with electrons in the negative energy state.
Yeah.
You couldn't actually get anything to go into a negative energy state.
Yeah.
But then, of course, he said, okay, there's a problem with that, because then that means that there should be a negative sign in the universe. So then he fixed that by saying there's a positive overlay or something. I forget how that fixed it.
Yeah.
But then basically what happened was that positive overlay, I believe, somehow was you were able to get that out if you could. So then he's predicted that she should be able to get. You should be able to get a positive charge out if you knock one of those negative energy electrons out from the vacuum, because you see that now the negative electron is now in the positive energy state, so you should have like a hole.
Exactly.
And he called those protons though, but they were actually antiprotons, and he is actually credited with the discovery of the antiproton that way.
Yeah, that huge leap in like.
So if that doesn't sound like crankology to you, then I don't know what can. I'm just like, what?
Yeah, literally, like full. What are you, bro? Your logic is so subjective that it's like, what are you?
It's adding on so many layers of just like things that can go wrong, but somehow through all of that, he got the answer correct.
That's just amazing intuition to me, because, dude, that's just insane. But
that's like, to me, it's like that can't be intuition though. There's something else operating at play there, because if you look at Einstein, the ultimate intuitive, his explanations were always so simple.
Yes,
and they always made so much sense in a very simple but brilliant way, and everything else would come from that simple image or diagram or thought.
Well, like he's done it so many times. The photoelectric effect. He's done it with
the whole reference frames in quantum.
Yeah, the thought experiments.
Yeah, and setting speed of light equal to c. It's just very simple changes or things that he did that gives you a whole rife
bag of just stuff you can work with.
Yeah, very true. Very true. He, there's a lot of those dudes. They just, I mean, they blow. They're the ones that make the biggest, like, these leaps in like logic, like those. They have these far out ideas almost. You know what I'm saying? Like Einstein and like Dirac and stuff, right? That try to build more like, more on the fundamental, asking why certain things are the way they are. Like the models that typically fail in physics are the ones where people try to ascribe certain preconceived notions
right
to physics, you know.
Right. I think it's much better when you let things unfold.
Yeah.
Which is kind of like the camp. I watched the Portal podcast with Eric Weinstein, and you can clearly see this between Garrett Lisi and Eric, because Eric.
Who's Garrett Lisi?
Garrett Lisi is the guy who came up with the E8 model of the universe. He's the surfer. You may have seen him back in like
2011 or something. It was like right the days when I was trying to get into
E8?
Physics.
It's E8 is like a special Lie algebra.
Oh, okay.
It has to do with mathematics shit that I have no
theory
zero
stuff.
about.
Yeah, exactly.
And it's just a name of one of the Lie algebras, the exceptional Lie group as they call it. I don't know if that's like a.
Is that a boy band? No, I'm just kidding.
It'd probably be a cool name.
Yeah. Hey, everyone with
like
the
a
Lie
K-pop
group.
band or something.
Yeah.
Yeah.
But Garrett Lisi is basically a guy who's kind of ascribing this E8 structure. He's using this E8. He's fitting physics onto the E8 structure, whereas Eric's trying to uncover it in a geometric form. So it's kind of those two ideologies that are in opposition, but I think both are useful, because both of them have proven successful during the time of history.
Yeah, true.
In making physics theories. So I mean, it's just two different ways of approaching things.
Yeah.
I tend to be in the uncovering camp, though. Flipping one stone over at a time, and then as soon as you flip enough stones, you take a step back and say, "Oh, there's a picture."
Yeah.
But yeah.
So that's pretty much it. I mean, is there anything else that you want to add on or something?
Not really. I had a whole. I think it's pretty much too late, but I had a whole thing on cold fusion.
Oh, really?
It's got a really, really cool, interesting story behind it.
Oh, does it?
That I never knew about until researching this. But
cold fusion could be its own episode.
Yeah,
almost.
we could do that maybe in another time, so I could save that as a
the
teaser for the
search for free energy. It's been
Well, this one's rooted in science.
Yeah,
real
I know.
Science.
I know, but I'm saying like
free energy was debunked in like fucking Aristotle days or something.
Yeah.
Maybe not true, but
no, but it's like, that motivates a lot of crank
time.
people to go into like cold fusion, basically fusion. Any sort of nuclear kind of physics is just like, they kind of
if
get
you're still
attracted to
exploring cold fusion in its conception, during the days of Fleischmann and Pons, and you're really fucking up. But they do have a cold fusion in existence today that's kind of like more serious. They call it like LENR, low energy nuclear research, or they call it like condensed matter nuclear research. And that has to do with things with like muon catalyzed reaction fusion.
Yeah.
And they're a little bit more credible, but they still haven't panned out. They're not really, they don't seem viable. But there is a like scientific form of cold fusion kind of still in existence today.
Interesting.
But yeah, there's a teaser maybe for next time.
Yeah, look for
one
that.
other podcast in the future.
Yeah, that'll probably be an episode. But yeah, anyway, yeah, I think that's it. We'll stay for the outro.
All right.
Thank you for making it this far. Please like, comment, share, subscribe. Follow us on Twitter.
Follow us on Twitter at
Yeah.
Eigenbros. Follow us on Instagram at Eigenbros.
Yeah.
Follow us on TikTok at Eigenbros2. Check out the website.
Yeah, and I have a question.
Yeah.
If you did make it this far into the video, leave a comment on maybe what would it be, like a fail? What?
Yeah, well, I think it'd be interesting to see what failed physical theories that the audience is interested in.
Oh, might know.
Or maybe even learning more. Maybe we could do a part 2 because there's a bunch more.
True.
So, yeah,
Very
guys,
true.
what failed physical theories are you interested in learning more about?
Or which ones are interesting, or which ones like maybe the logic is interesting.
Yeah.
Right, because the logic to me was interesting for the Schrodinger one. I'm like, oh, that's kind of true. Yeah.
Yeah.
It's
Yeah.
like, yeah, you would expect that, but along those same lines, maybe you have something that appeals to your sensibilities.
So leave it in the comments below, guys, and we will see you next time.
Yep.